Hi and welcome to my talk about the intricacy of tasks. My name is Leonard Eberding. This work has been done at the Reykjavik University at the Center of Analysis and Design of Intelligent Agents, short CADIA, together with my colleagues Matteo Valencia, Arash Shaikla, and Kristen Thoresen. Before we start out, I want to show the outline of this presentation. So first of all, I will present the motivation why we need what we present here. What does it mean for us in the research community before I move on to the causal principles of tasks? So this intricacy measure is based on causal principles, so I will present them very shortly. For one, causal relational models, and for another, causal diagrams. Before I then move on to the intricacy and difficulty definition, this is split into three different parts. One is the definition of intricacy, then we come to the effective intricacy, which includes the agent itself, and then the difficulty of tasks for a certain agent. Then we will talk a short while about learning and performing. So what does all of this mean? How can we use this for us in the AI or AGI research community? Before then, in the end, I will conclude on this talk. So motivation, why do we need this? There exists currently many different evaluation platforms, and all of those focus on different things, and they show different results for the same learners. And generally speaking, we can't reliably compare results between different evaluation platforms. So if we look, for example, at the arcade learning environment or the OpenAI Gym or the Malmo platform, maybe some agents reach a similar performance in different evaluation platforms, but generally speaking, there's no cross comparability. And sometimes we even have the problem that even in a single platform, we can't really draw conclusions on the progress of AI, as has been shown using item response theory. This all leads to the inability to assess the progress of AI or AGI, and calls for a measurement that can be used platform independent, such that such an assessment is possible. This measure we introduce in this talk, and we think of it as the complicatedness of tasks, or as we call it, the intricacy of tasks. So what do we need to describe such an intricacy or complicatedness of tasks? It's causal principles. We only take the most fundamental assumption that we can take, which is that there exist causal relations. This is why we put a focus on this. With causal relations, we do not mean an axiomatic truth to what's out there in the physical world, but rather that we have rules in our environment, which can be translated to something leads to something, or A leads to B. If there were no rules, we could not learn. So I think this assumption is really one that can be taken unproblematically. Additionally, as a little side note here, what we have to take care of is that the body is part of the task environment, not of the controller, and therefore it must be modeled by this intricacy measure as well, so transducer imprecision must be taken into account. To describe the causal relations in an environment, we use causal relational models, or CRMs, which are bidirectional models, which give us the ability to, or provide the ability to forward chain to do predictions, or backward chain to create paths to goals. Each of those CRMs is a relation between two different patterns on the left-hand side and right-hand side of this model. The left-hand side is a pattern representing the cause, which is usually a discrete event, like a change in a variable value. And the right-hand side is a pattern representing the effect. The CRM itself then represents the relation between the left-hand side pattern and the right-hand side pattern in such a way that it enables this bidirectional usage of forward and backward chaining. Additionally, there exists a set of requirements under which CRMs hold. and those represent the context and the relevance of each CRM. We can then go on to causal diagrams. So if we look at the task from the designer's perspective, which is to be thought of as an omniscient point of view, so we as the evaluators might know or should know what the task is built up from. And if we do this from the designer's perspective and analyze a task, we can come to weakly connected causal chains of different variables. So this reduces a task to its deterministic form, which can then be represented using those previously described CRMs. Additionally, where now the body of the agent comes in, we have to model transducer imprecision. So variables are not directly observable or manipulatable, but rather through causal children or parents in the manipulation case. So on the right here, you can see such a weakly connected causal chain, and the red bubbles are the manipulatables, which are not really part of the environment, but rather are still inside of the controller. And in green, you can see the observables. So it is the difference between, for example, the actual signal reaching the controller and the light hitting the camera. We're not really measuring the light, or the controller does not really receive the light, but rather the signal from the camera. So this is how we model this here. So now we come to the important stuff, the intricacy and difficulty, where this all leads to. So what do we mean by intricacy? As I said earlier, we defined intricacy as a measure of a task's complicatedness, and as such, we can use it to analyze tasks, rank them by their intricacy value, and get a general overview about the complicatedness of different tasks on different platforms. Additionally, this gives further implications for any AGI aspiring system when it is learning or performing a tasks. And to describe this complicatedness, we differentiate between three different things. One is the intricacy, which is really only an objective measure of the task environment itself. The effective intricacy, which takes into account the agent's background knowledge, and difficulty, which is a combination of intricacy, the task environment, and the agent itself. So first of all, what do we mean by intricacy? Intricacy is a multidimensional measure, which consists of three different parts. First of all, the minimal number of causal relational models, which are needed to represent the relations of the causal structure, which stands in some relation to the goals of the agent. So this also means that the level of detail of a task is of importance. So it makes a difference whether you describe a task in the sense of, for example, a wayfinding task in the sense of rooms or cities, or even the motor controllers or commands to motors, the joint angles of certain joints of the agent or of the body. It makes a difference in which level you describe a task. Then the next part is the number, length, and type of mechanisms of causal chains. So if we think about the CRMs, which are the relation between the left-hand side and the right-hand side, it is of importance what this relation is. Is it linear, nonlinear, highly nonlinear, discrete? We have to take this into account. And then lastly, the number of hidden confounders which influence the causal structures. So the more hidden confounders we have, the more complicated the task becomes. In other words, the intricacy of a task is a measure of physical mechanisms. So it is independent of the architecture, the knowledge, or the capabilities of the agent which performs the task, but rather only describes the task in its environment. The effective intricacy now takes into account the knowledge of the learner. So especially when we're talking about AGI system, about cumulative learners, which gather knowledge over the lifetime, we have to think about how can we describe the task's complicatedness in relation to what the agent already knows. So this is what we use effective intricacy for. it comes down to the same points as earlier, but now we are only talking about the unknown causal relations, the unknown mechanisms of causal chains, and the unknown hidden confounders. So it is really just the intricacy minus the knowledge of the learner. And then difficulty is, again, a multidimensional measure which takes into account the effective intricacy of the task, so including the background knowledge of the agent, the controller's ability to learn. Now it becomes interesting because something is more difficult if the agent cannot learn well. Tasks just generally become more difficult. And also the transducer imprecision and the available resources, which are primarily time and energy in this case. And all of this then makes up together our definition of difficulty. So the difficulty can be expressed as a function of the controller itself, and the task environment, which then consists of the intricacy of the task, the resources available to the agent, and the noise on the transducers. Now, what does this mean to us for us researchers? So, first of all, we can define things that might seem obvious, but which are hard to properly define. And this is then by learning, things become less complicated in a subjective matter of the agent. So by learning, the effective intricacy is reduced. Changing the goals in the same environment, however, does not necessarily affect the effective intricacy. Causal relations are usually independent of the task. They exist in the environment no matter which goals are given to the agent. So if we take the physical world, there is physics happening no matter what your goals are. So the only thing that can change is the relevance of variables. So whether I need them to achieve a goal or not. The next thing is that we can state that when a learner knows all causal relations of a task environment, the energy and time required to perform a task become the decisive measures of difficulty. So if I have to get to San Francisco in an hour here from Germany, it will be impossible, not because the task is so hard, because I know what I have to do, but just because I have insufficient time to do what I have to do. So then it comes down to that if time and energy are sufficient and the learner knows all causal relations, then the noise from the transducers becomes the only remaining part of the computed difficulty, which we believe makes sense. Also, we can say that a controller that performs a task repeatedly perfectly, the effective intricacy of this task is 0. So the higher the effective intricacy of a task, or the lower the amount of experience that the agent has on this task, the more difficult the task becomes, if we take all other things being equal. And if we go all the way up to where the effective intricacy is equal to the task's intricacy, then we, or the agent, needs to rely on completely random interactions until it has extracted enough CRMs or knowledge to reduce the effective intricacy. So if everything is new to the system, it must do random interactions. And I think all of those points are nice to have defined in a way that we can actually talk about them and use them in our research. So concluding this presentation, we introduced a new measure to objectively describe the complicatedness of tasks. Of course, there's still work to do. So, for example, to automatically compute the intricacy of different tasks. For this, we suggest or are aiming to use the AGI aspiring system ERA from Reykjavik University as well. Since it already uses CRMs for knowledge representation, we believe that we can adjust it in such a way that we can automatically compute the intricacy of different tasks. Also, we are planning to test this intricacy measurement on the tasks of different evaluation platforms, for example, the arcade learning environment, where those tests I mentioned earlier with doing item response theory has been done on. And we hope then to compare our results to the ones done by using item response theory so that we can see whether we find similarities or correlations between our approach and the others. We also hope to compare it to the actual results of different learners so that maybe we can see that the performance on different tasks really depends on the intricacy of the task. And then lastly, we hope to be able to connect the generality of a system to the intricacy of the tasks that it is able to solve. So instead of just having single tests like the Turing test, the Loveless test, the Wozniak coffee test, or something like that, we hope to really describe the generality of an agent in a sense which is objectively measurable by the tasks it can solve. This would be a huge step forward for the AGI community, I believe, that we can actually say which agent is more general than another. And with this, I want to thank you very much for listening in on this presentation. Here are the references used for this talk, and I'm really looking forward to the conference and hope to see you all soon. Thank you very much, and goodbye.